Hi, welcome to the Calculus 2 lecture series. And we are in the first unit of Calculus 2. We are talking about the applications of integration. And this is our second lecture, the second part of the second lecture. We are going to find the volumes. And so in this lecture, we're going to take a look at what is the disk or the washer methods, how to find the solid when we have a function, rotating around certain lines here. All right, so now let's go to our lecture notes and let's go ahead, start here. Okay, so the first things here, so for this lecture, the second part of the how to find the volumes here. So for this lecture, the key concept, we're going to talk about the two things here. Basically, we're going to see how to find the volume of a solid revolution. Right? So the other ones here, we're going to introduce or try to learn what is the disk, or sometimes we call this the washer methods here, how to find the solid here. So what is the solid revolution? So the solid revolution basically is like if I have for examples here, let's try to do example here. So if I have a kind of a functions here, right? So let's see here, if I have a functions and this is my functions here, right? So this is my f of x function. Then, the solid of revolution, that means if I rotating this function along like some lines, so like in here, we say let's rotating around the x-axis. So if you're rotating here, so what you will get here? So you will get a solid here, right? So that's what, now I want to find the area. So can you visualize it? So this is kind of like when you're rotating around the x-axis, so you will get a solid kind of like a cone, but it's not a total like a cone, but it's a kind of a solid thing. So we want to find if in this situation, how do I find how do I find the volume? Also, like in here, right? So in here we say, okay, so the same functions here. So if this function here, right? So this is my f of x function. I can also rotating around the y-axis. So if you're rotating around the y-axis, sometimes we put these notations here. That means, okay, so I hope that I draw it good. Okay, so this one is here, right? So that means I typically say, okay, if you see here, this is rotating here, right? So if you're rotating around the y-axis, then we generate this solid here. And now I'm going to find how to find the volume for this solid. And then when you're rotating, you're not necessary, going to rotating on the x or y axis here. So for example, here, and so like let's take a look for this ones here. If I have a function go like something like that, all right, and so from here to here, so if I were looking for the area from here to here, the rotating this area, but instead of rotating around the y-axis, I can say, hey, I want to rotating around the -1. Okay, so this lines here, right? So this is x equal to -1 line. I can rotating around these lines here. So basically you shift your y-axis, right? So for these ones here, how do you rotating here? So that means in here, like this one, okay, so you're going to rotating over to over here. Let me try to, okay, so it's going to be over here. Okay. Okay, so basically what we did here is like now you are rotating around the x negative. So basically, you shift the origin, to here, right? So you basically, the shift that, and so you will have like one distance away. So basically you do like this. All right. So now if this is the air, if this is the region you try to find here, right? So like in here, so basically you are rotating here, all right? So that is the volume we try to find, and we're going to do a more this type of example. I just show you in here. You can talk about you not necessarily you're going to rotate around x-axis, y-axis. You can rotating around like any other line. So like x equal to -1, or you can like shift the x-axis, right? So this is your shift the y-axis. Okay, so we're going to go over each examples here. Now let's take a look at how do I do the rotating around the x-axis? What is we call this the disk methods here. Just like we did on the previous here, right? So in here, I show you, okay, so here, this line is not too straight. All right, so here, all right. Okay, so in here, like we just talk about here, so if I have a function like this, right, this is my f of x functions here, and I want to find the area from the maybe a to b, and so this is f of x. So when you're rotating around the x-axis, that means you are rotating here, so you will generate a kind of the cone here, right? So basically, so this is kind of like we just use this notation to represent so you can see, so can give you a better visuals here. So I want to find the volumes here. So it's very similar to what we call the Renaissance here, right? So if you cut a slice, cut a very small slice here. Okay, so now let me see here. So if I cutting, let me use a nice color here. All right. So if I cutting a small slice here, all right, so if I cutting a small slice here, so this distance I call the delta x here. So this small slice, as you can visualize, is what? It's a cylinder, correct? So this small slice will be a cylinder, something like this, okay? So it will be something like this, right? So can you visualize that? So it's kind of like a small cylinder. It's very, very thin cylinders here. So we know how to find the volumes of these cylinders, right? So the volume of this cylinder will be, this is just, we need to find the area. So this is what? Pi r square times the height. The height here is this the thickness of this cylinder, so it's a delta axis here, right? So now what is the radius? Radius of this circle, when this is what we call this disk method, is when you slice it, each one is a solid disk, right? So what is the radius here? The r, the radius is what? Radius is these functions, right? So whatever in here, the f of xi, so if this point is xi, so the radius will be f of xi stars here. So for every point, so like this point is xi star, so the radius will be f of xi star. So by the Renaissance, so for each cylinder, the volume will be pi r squared. So it's pi r is what? F of xi what? Squares, right? So pi r squared and then times the height. So what is the height? It's a delta axis, right? So this is, so if you add all those small pieces together, right? So this is I from 1 to n, and so the, okay, let me put it this way here. So if then you add all this, right? So I from 1 to n. So this is the approximate solid, right? So by the Renaissance concept, if you continue slice and slice to many those thin slice, so what is the volume? So this summation will become what? Will become integrations, right? So this integration is whatever this is solid locate, like in here, if the solid want to be, you know, from the A to B, so if this is A, this is B, then you only you only sum like this part, so it will be the integrator A to B. Then the pi r squares, right? So you generalize the f of x squared dx here. So this is what we call this the disk method. Is pretty straightforward. So basically you see that and then you slice it, you're going to get a solid disk there, right? Okay, now let's take a look at this one. Okay, so this one's here. This one is pretty simple. So first things I always encourage the student, you know, maybe you can graph it or probably will make your, you know, visual is a little better. Okay, so this is the y equal to the 4 minus x squared and the y equal to 0, x equal to 0, x equal to 2. So this is a quadratic. So when x equal to 2 is 0, x equal to 0 is 4. So it's here, right? So your function is something like here, right? So it's a quadratic function bounded by y equal to 0. So that means is bounded by here. So this is the you know, this is the regions, right? And then you are going to rotating this region along the x-axis here. So if I'm rotating, so you can put like some notation like that. So if I rotating, I will usually like use a dot, right? So that means that what is my rotating here. So as you can see, and then you are going to find the solid of this rotations here. So it would be better if you put it like this way. So it's kind of like put it like this, right? So you will see it's kind of give you a better visuals here. Okay, now let's take a look, just like what we did before. Now I'm going to slice very thin slice of here. So as you can see, you know, I hope you can visualize here the thin slice here, it will be cylinders here, right? So where is the radius? The radius is from here to here. And then this functions here, this is my f of x functions, right? So the radius is what? F of x. So what is here is 4 minus x what squares, right? Okay, so now I can, you know, I can integrate. So the regions here is what? So what is the volumes here? Volumes here is from 0 to 2 pi r square, right? Pi r square, try to find the area of this disk then times the height. So r square is what? Is 4 minus x square to the square, then the dx. And then now this one will really just become like a very straightforward integration. So this is 0 to 2 pi. Then you can fold this. This will be 16 minus ax squared plus x4 dx, right? So now this will become very straightforward, the integration, and I'm not going to, you know, work on the detail, just, you know, so after you do that, this will be the 215.6 over 15 pi, right? So this will be the volumes for this solid here, okay? And now let's take a look here. The next one's here, rotating about the y-axis here, all right? So for the rotating about the y-axis. Okay, so it's the disk method, so it's the same things here. So that means if I have a, okay, so if I have a function, so right now, let's take a look if I have a function like this. All right, so I'm going to find the rotation about the y. So that means I'm going to rotating here. Then it will be better if, you know, so if this is the area I'm finding, right? So if this is the area I'm rotating, so that means this is the solid I'm trying to find here. So it's just like we rotating along the x-axis. So when you slice here, right? So when you slice it, you will get a cylinder again. And what is the, so this distance will be what? This distance will be your r's, right? So this distance will be your r, and this distance is x. So in here, instead of the function like f, you know, the instead of the function y equal to the f of x, so we need to change this function to the x equal to some function for y's, right? Because that's what we are rotating around the y-axis, and we want to find the pi r square. So it's the same ideas, right? So you just like you just summation all your disk, right? From from 1 to n, pi r square. But what is the r? R is the x value, so it's gy, right? So it's gy what square, then delta y, right? So the thin slice. So now if you use the Riemann concept, when you slice the infinity number of the slice, so this summation become the integration. So will be the a to b pi, what is here? Gy square and the dy here. All right, so that is what we call the disk method for the y. So let's take a look some examples here. Okay, so this example we say set up a definite integral for the volume following the solid revolution, and for the region of y equal to the square root of x, x equal to 0, y equal to 4, about the y-axis here, okay? Like I say, I always encourage the student, first thing is to graph, right? So y equal to the square root of the x, so x equal to 0, y equal to 0, y equal to 4, so the y equal to 4, then x equal to 16, right? All right, so here, so basically y equal to the square root of x, so here. So you will have, like this is my square root function, so let's do a better pictures here. So this will be my square root function. And now they are trying to bound it with y equal to 4. So here, this is y equal to 4. So let's say bounded by this function, x equal to 0 and y equal to 4. So basically, you know, I will encourage a student, you always like highlight. So this is the regions I want to what? I want to rotating. Okay, so now let's rotate here. So rotate around the y-axis. So put a notation here. I hope that I'm doing good in this. Okay. So this, I run out of the space. So here it's kind of like, but you know, if you kind of do that, so you can kind of visualize it's kind of like that. So this is the solid we are looking for here, right? So it's kind of like, okay, so now the same way, I'm going to cut a slice here, right? So I'm cutting a slice. So this slice, what is here? So this is the radius, right? So I want to find the x value. So if I want to find the x values here, so I know the y equal to the square root of x. But now, since this is my radius, right? So it's the x value. So the x is equal to what? Y squared. So this is what? This is my radius here, correct? Okay, so now by using that, the Riemann-Sum concept, so it's going to integrate from 0, because now in here, take a look here, because I'm integrating to y, so y is to 4, right? So when x equal to 0, y equal to 0. Okay, so my integration will be 0 to 4 here, pi r square. So pi r square is what? Is y square. This is radius r to the square dy here, right? So this is also become a super easy method. You know, integrations here is y4 dy, and so if you do the simple integration, so the answer will be 1024 over 5 pi here. Okay, so now in here, you know, one thing's here, let's take a look here. So if you are rotating along the y-axis, you are, when you use the disk method, you are integrating respect to the y variables, right? So if you are, you know, rotating about the x-axis, you are integrating along the x variables here. Okay, so now what is the wash method here? So the wash method is just similar like the disk methods here. So let's take a look at the wash methods here, right? So the wash method, let me show you a graph here. All right. So for example, here I have two functions here. I have a, well, let's say here, this is my f of x functions. And then here, this is my gx functions here. And I have a region. So this is A and this is B here. All right. So I am going, so this is the regions here. It's bounded by these two functions, right? And now I am going to rotating this region along the x-axis, all right? So we can always do the similar like the y-axis. So in here, so if I rotating, that means my rotating what? I'm rotating this g-axis here, right? So, right? Then I'm also rotating this f of x here, right? So this is what I'm rotating here. All right, so this is still my regions here. Okay, so take a look here. So for the, you know, for these big ones here, the, you know, for the f of x, when I rotating here, I'm generating this areas, right? This red one. Okay, and then the solid I'm looking for is rotating is this ones here. Then for the green ones here, when I'm rotating here, take a look what the, you know, the what I'm generating here. So I'm generating here, right? So here, this is the, did you see here? Right? So this is the little disk I'm generating. And now if you are cutting it, right? So let's see here. So if I am cutting a slice here, so if you take a look at this one, so the blue one, if I'm cutting a slice here, but the yellow area and when you're rotating area, the yellow region, the the solid generated by this yellow region is only these two pieces, right? So when I slice this ones here, the blue one, I get the big slice. So there's no volume in between here. So I need to minus. So this is what we call this, the washer. You don't really, cut a disc anymore. You are cutting a what? This is what we call this washers, right? It's kind of like a donuts, right? So it's kind of like a donuts here. So now from the washer methods here, so the volumes here, we still do the same. So we say, hey, the volumes here will just be, I'm taking a look at the big disk on the outside, right? So the big disk outside is what? Is a pi r square. So what is the big disk outside? The radius is f of x. So this is f of x squares, right? So this is the, so the big donuts here. So this is f of x. So then you minus pi, the small one, so it's gx squared, right? So the inside, see here, the inside is here, right? So the radius is here to the gx. I'll try to color coding that. All right, so now I'm just integrating same things where you want to go, a, b, and the dx here. So you can do the same things for the rotating along the y-axis here. Right, so it's the same thing. Okay, now let's take a look at this one here. The example number 3 is here. All right, so the number 3 is here. So the solid obtained rotating the x-axis of the region. All right, so let's, like I say, I always encourage you try to graph. That will give you a very good idea. Okay, so now in here you have the solid. So y equal to x cubed. So y equal to x cubed is a function like this, right? So for this ones here, because y equal to the x cubed, so this is the y equal to the x cubed. All right, and the y equal to 8, y equal to 8, so y equal to 8 here. So hey, so what happened here? So this is the region. So I always say you graph it so you will get a good idea how to do that. So this is the region I'm trying to rotate in, correct? Okay, so now I'm rotating along the x-axis. So that means I'm rotating here. Go down here like this way, right? Okay, so here this is the, right? So here, all right. Okay, so basically now you are here. Okay. I'm looking for the solid generated by this yellow region. Okay, so now take a look at this rotations here, right? So I'm doing kind of put circles here, so you know I'm rotating here. Okay, so this ones here is what is we generate, but I'm looking for the yellow one. So that means, okay, so let's try to cut us. So if I'm try to cut a slice here, all right? So when you try to cut a slice here, I'm only, wanted this yellow, yellow volumes here. So the first things here, you say, okay, this one's here, but for this discs here, right? I am, including this small regions here, right? This one's here. I don't have the volumes here. Okay, so let's take a look at here. What is the outside circle, the red one here? Maybe, I think I don't know, I can maybe I can do a better way, move the circle a little bit out. Maybe that will be better. Sorry, I kind of erased everything, but that's fine. We can because I want you get a better visuals here. Okay, so here. Okay, so now let's try to cut a circle here. All right, let's try to cut a disc here. Okay, so when you try to cut a disc here, as you can see, right? And this part of the disc does not have a volume, the green ones here. So in order to get the yellow volumes here, so the first I need to pi r square. So the big circle, what is the radius? The big circle, the radius is from here all the way to here, right? So the radius is what? The radius is 8. So it's a pi r square. So it's pi. Yeah, so don't. Okay, so I'm trying to color coding that. So pi r square. So the r is what? Is 8, right? So it's a pi r square 8. So it's a constant because they all reach here. So this is a dx. And then I need to minus this green little disk. So the green, the radius is all the way from the axis to these functions, right? So I'm going to minus, okay? So I'm going to minus pi r square. So what is the radius of this green one? It will touch these functions, right? So it's x cubed to the square, correct? Because that's the radius. So this is what? The dx. Now what is the x value? X is from 0 all the way. What is the value? We'll give the y equal to 8, x equal to what? It's 2, right? Because you're solving y equal to 8, so x equal to 2. So you integrate from 0 to 2. Then this become a pretty straightforward integration. So this will be 64 pi minus pi to the x to the 6, then the dx. So I trust you have the ability to carry out this integration. So this integration will be 768 pi over 7. Okay, and okay, so that's it. That is what we talk about the disk and washer method. So I like to take a break here and go to our second videos. And we're going to talk about how about now I'm not rotating along the x-axis and the y-axis here. I'm rotating about a lines here. Now, how do I do the disk and the washer method? All right, so nice talk to you and looking forward we continue these lectures here. Okay, talk to you later. Okay, bye-bye.